Hello. Okay. So we're back. And we're going to be looking at a couple of examples. Okay. So our first example, that's not what I wanted to do. Okay. So our first example is, so if we know that the function f, we've got a function f from x to y is invertible, then the image of f is y. In fact, what we need to know is for every b in y, so we're going to say for every b that's in y, there exists one and only one x in x such that b equals f of x. And then we can write that is that x is going to be inverse f of b. So b is equal to f times x, which is f inverse of b, right? So this is pretty simple. It sounds complicated, but really, so it's saying if it's invertible, right? Then in other words, it's just giving the definition of a function. It's giving the definition of an invertible function, because it's kind of saying that there are unique values, and that's what makes it able to be inverted. So I'll kind of say it again in case you didn't get it the first time. So basically, if a function f from x to y is invertible, then the image of f is y. In other words, all of the possible outputs of f are y. And indeed, for every b that exists in y, there is only one x in x such that b equals f of x. And we can sort of write this in terms of inverses because we know that x is going to be inverse of b. So we can write b is equal to f of x, which is equal to f of inverse f of b. An image might help with this if you didn't get that the first time, because we've got x, we've got y, we've got some dots on both sides. So if we take this random dot right here, switch colors, this is x. This x is equal to f inverse of b, right? And this is b, right? And there's just like the one unique value there. Because, we already talked about the idea of inverses is that there's only one unique value. Only one thing can lead to one thing. Because if there are more options than that, then you can't really switch around. You can't really inverse it because there are more than one option. So yes, again, this fact is only true for invertible matrices. So next, we're going to kind of do something a little different here. We're going to go really general for finding image and then go very specific. So we've got a linear transformation T. That was a horrible T. We've got T that goes from R3 to R3. And this linear transformation projects vector x orthogonally onto the x1, x2 plane. Another way of writing this is that T of x1, x2, x3 can be projected orthogonally to lead to it being on the plane x1, x2. And of course, there'd just be 0 down here. So if we draw this, you've got some x, and it's orthogonally projected onto this plane. Right? T of X. So what's the image? The image is going to be this. Right? The image is going to be this plane. There are a couple ways we can think about that. The first is that we can just say that, you know, there is an X that will lead to every one of these Y's that is on this plane, right? There's an X that will lead to this Y, an X that will lead to this Y, this Y, this Y, this Y, this Y, you know, just anything on here. Another way that we can think about this is that I believe, remembering from a couple lessons ago, orthogonal projections are invertible, right? They're invertible matrices. And if that's true, we kind of already learned that if the function f from x to y is invertible, the image of f is y, right? So the image of f is this plane right here. So that was a really general example because we didn't have any numbers, right? We just had a random vector. But how would we find the image once we actually have real numbers? So we want to describe the image of the linear transformation T of vector x equals A times vector x from R2 to R2. But here's the difference. We're given that A is equal to 1, 3, 2, 6. Well, here's what we know. We know that the image consists of all the values of T. Well, what would all the values of T be? Let's think about that. Let's plug in what we know. We know that T of x1, x2 equals A of x1, x2. And furthermore, that's going to equal 1, 3, 2, 6 times x1, x2. But now if we split this apart, so let's split this into column vectors. We can say x1 times 1, 2 plus x2 times 3, 6. So what is the significance of doing this? So if you think about it, we've got two vectors here. We've got 1, 2, and we've got the vector 3, 6, right? And then we've got these two x's. So if we think about this in a plane, if we just think very generally, let's think about vectors. We've got two vectors. They make a plane, right? As long as they're not parallel, they make a plane. And then you can multiply each of them by scalars, these x's 1 and 2, to get, you know, a certain length. But the point is that they make a plane. And the idea is that the image is the span of this plane. We'll get to the definition of span, but span basically just means like any point along the line made here. But it's the image is everything that falls onto this plane that is spanned by these two vectors. Now, this example is actually a little strange, and you'll see why in a minute. Because what we can say here is because we've got 1, 2, and 3, 6, we can actually say x1 times 1, 2, that doesn't change, plus 3x2 times 1, 2. What does this mean? In other words, these two vectors are parallel. They're parallel to each other. So we can pull out the 3, we can make them equal each other. We can write this in another form by saying x1 plus 3x2. Now, you might be thinking, you know, what's the significance of the x1 plus 3x2? Just treat this as any scalar, right? Because we can have any scalar here. We can have any, we're just going to say k here, times this vector 1, 2 is equal to the image. So instead of having two vectors that form a plane, we actually have 1 and then anything that's parallel to that vector, right? Because 3, 6 is parallel to 1, 2. So the image of t is the line of all scalar multiples of the vector 1, 2. And the way that you can draw this we've got 1, 2, we've got 3, 6, etc. But now parallel is it's a little different, right? It's a little strange. And so we can take this method and really apply it to non-parallel examples, which is kind of what you're going to find more commonly. The point is you split the matrix into its columns. You multiply that times the scalars or the different components of your X vector, right? And the image becomes the plane that is spanned, or the plane that falls within these vectors that you have, that you've split it up into. And of course, you also have to take into account that it's the span of these vectors. In other words, any scalar multiple times these vectors falls on that plane. But that's sort of our next example that kind of goes a little more specific. So there's another example that I've got here. That's not parallel, which is kind of helpful, where we're moving from R2 to R3. And we've got the A equals 1, 1, 1, 1, 2, 3. I'm going to skip a couple of steps here. Move a little quickly just to kind of show this idea. But the point is, we've got x1 times 1, 1, 1, because we split up into column vectors, plus x2 times 1, 2, 3. So that means that the image is all linear combinations of these two column vectors, or in other words, the span of these two vectors. But of course, we'll get to that. But the way we would draw this is we've got, and of course, we're going to call this one V1 and this one V2. We've got V2, got V1. It makes a plane here, but then it gets extended out, right? Because again, linear combinations, you can multiply it by any scalar and have it still fall within the image. But this plane, of course, it's centered at 0 at the origin. This plane right here is the image of this. Okay. I'm going to next talk to us about span. Yes, we're going to talk about span. So what is span actually? Okay. So they've got a theorem for this to explain what span is. So if we consider the vectors v1 through vm in the subspace Rn, the set of all linear combinations C1, and C1 is just standing in for any scalar, C1 times V1 plus all the way out to Cm times Vm of these vectors equals their span. So span is really just a way of saying linear combination. So we can then write image thinking about span. So we can say that the image of a linear transformation is the span of the column vectors of A. So let's write this. Image of A equals span of CV, which stands for column vectors of A. And this right here is, I think, the most useful theorem because it shows you how to actually find the image with real numbers and stuff. Okay. So we can prove this. We can prove it really easily. Because if we say that A times X is equal to these column vectors of A times X1, Xn, that's going to dot out to a linear combination, right? And if we say that AX equals a linear combination, well, we know that T of X, A of X, whatever, that is the actual image, right? We know because we're looking for the outputs that are possible, and AX is our output, or A times vector X is our output. And so if A times vector X is equal to this linear combination, and that linear combination can also be written as the idea of span, then span of these column vectors is going to be our image. Okay. So there are some properties that we need to know for the idea of image. So the first property that's really important to keep in mind is that the zero vector in Rn is in the image of T. And I'm going to prove these in a second. Second, we need to know that the image of T is closed under addition. In other words, if V1 is in the span, or if V1 is in the image and V2 is in the image, V1 plus V2 is also in the image. And we can say it's also closed under scalar multiplication. Right? What does that mean? Same thing. If you have V1 is in the image, V2 is in the image, V1 times V2 is also in, or sorry, closed under scalar multiplication. That's not true. If V1's in the image and K, scalar K is in the image, then K times V1 is also in the image. I'm going to prove these really quickly. So for the first one, the vector 0 equals A times 0, right? Because A times 0 equals 0, which can also be written as T of 0, right? So if T of 0 equals 0, then that means it's got to be in the image because, and I believe I'm going to have to check with Dr. Prudhomme on this, but for these next couple of proofs, I believe what they're saying is that we can, if we can kind of prove that a value is within, can be put as an input of T and lead to a certain output, then that means that output is in the image, right? Because, you know, we know obviously we can plug T of 0 in, and we just kind of proved that T of vector 0 equals vector 0, right? So we know that that output is possible for the linear transformation of T. And if we know that output's possible, then that means it's in the image. So the next idea is kind of if we've got, let's say we have V1 being equal to T of W1. And they've got V2 is equal to, surprise, surprise, T of W2. If we add these two together, we get that V1 plus V2 equals T of W1 plus W2, right? And then and sorry, I kind of skipped a step there because really you would start out by separating these things. So you have T of W1 as its own thing plus T of W2. But then of course we can combine those things just based on the sort of rules of addition and like the rules of algebra, right? And again, we sort of proved that these inputs lead to these outputs. And so those outputs are then possible. So V1 plus V2 is in the image. And then we can finally do this for if we say that V equals T of W, then K times V, it's going to equal K times T of W, but then we can kind of do our fancy little switcheroo. Because it's a scalar, we can move it around, it's commutative. So we can say that K of V is going to be equal to T of KW. And again, since we've proved that this input leads to this output and that this input can work, then that means that this output also works. So that's in the image. And of course, it follows from these two properties that, so if the image of T is closed under addition and closed under scalar multiplication, then it's also closed under linear combinations, because a linear combination or a span is really just a combination of addition of vector addition and scalar multiplication, right? And then there's sort of one last little proof that I'm going to do before we move on to talking about kernels. So this proof is we're considering an n, okay. We're considering an n times n matrix. What we want to show is that the image of A squared is a subset of the image of A. And I kind of like this proof because it's kind of one of those ones where it's like cool logic and it's a little tricky. But sorry, if you didn't kind of figure out what I meant by subset, is that so each vector in the image of A squared is also in the image of A. So let's say we're going to say that we've got vector B, and we're going to set vector B equal to A squared times vector V, which is also the same thing as A times V, right? And that's in the image of A squared, obviously. So we can also write vector B as A, and then we can use association to say A V. And what we can do here is we can turn this AV into vector W, right? We can combine this and say it's A times vector W. If we've got the equation B is AW, well, see, that shows that B is in the image of A, right? Because we've sort of written this A squared in sort of a form that fits the image of A, right? The image of A is all of the outputs that are possible, right? So that's going to be A times a vector, and we've managed to turn A squared V into A times a vector. So that means that we've just proved the theorem, right? They kind of drew a little diagram to help us with that, but I don't think it's really necessary. The overall point is that the way we proved that the image of A squared is a subset of the image of A is that we took A times vector V, and we turned A times vector V into a vector itself. And then of course, the image of A is going to be equal to A times a vector. And we've just kind of proved that A times vector V can be turned into a vector. So that's kind of a tricky little theorem. And I understand that a lot of these explanations, I kind of go through them quickly and I use a lot of words and it might be a little confusing, but that's kind of the basic idea. And then I'll be back in a second with kernel.